Module 8, Work and Energy, Introduction. In previous modules of this course, we spent a lot of time discussing motion. We used our one-dimensional motion equations to describe and understand both one- and two-dimensional motion. We then used Newton's laws to better understand why motion occurred according to our equations. Finally, we even studied circular motion and how it applies to gravity. It's time now to discuss something that affects all of these subjects: energy. Without energy, none of these things that we have discussed so far would ever occur. As a result, the fundamental concepts involved in understanding energy are some of the most important concepts that you will ever learn in physics. Indeed, the fundamental ideas that scientists have developed about energy have probably done more to help our understanding of creation than any other set of ideas. Obviously, then, it is important for the physics student to explore these concepts extensively. The definition of work and of energy. If you've already taken a good chemistry course, some of the things discussed in this section should just be review. Nevertheless, there is probably a lot here that you haven't seen before, so pay close attention. First, if we are going to talk about energy, we had better define it. Energy is the ability to do work. This might seem like a silly definition. After all, what's work? Well, physicists define work as the follows: the product of the displacement of an object and the component of the applied force that is parallel to the displacement. If you think about it, this definition of work is much more restrictive than is our everyday usage of the word. For example, suppose you're trying to move a large rock in your yard. You push and you push and you push and you push on the rock, with all of your might, but the rock does not move. In the end, you give up. You are totally exhausted. Have you done any work on the rock? You think you have, but by the definition given above, you really haven't. You see, in order for the work to occur, there must be a displacement. In addition, the work that is actually done is calculated by determining the product of the displacement and the component of the force that is parallel to the displacement. So in pushing on the rock, you were indeed applying a force, but the rock did not move. So you were applying a force, but if the displacement was 0, there would still be work, there would not be work, because anything times 0 is 0. Thus, there was no displacement, and as a result, you actually did no work on the rock. Now, remember, energy is the ability to do work. Thus, energy is the ability to apply a force, which results in the displacement that is a component parallel to the force. So if you push a rock with a force, and if the rock moves so that at least a component of its displacement is parallel to the force, energy has been expended. You need to remember, however, that energy is the ability to do these things. In order for energy to exist in a situation, the application of the force and the displacement do not have to actually occur. The ability for the application of the force and the resulting displacement is really what matters. So this is a very important point, and we're going to come back to that in a minute. Although I have already given you the definition of work, I want to show you how we define it mathematically. After all, physics does us little good if we cannot take the concepts that we learn and apply them to specific situations. That's what the mathematics allows us to do. So right now we're going to be talking about equation 8.1. And this equation, W represents work, delta X stands for the magnitude of the displacement vector, and F, parallel, is used to indicate the magnitude of the component of the force vector that is parallel to the displacement vector. Please note that this equation assumes the force applied is constant throughout the displacement and that the displacement occurs in a straight line. If the force is not constant, or if the motion is not in a straight line, work can still be calculated, but you cannot use this particular equation. All right. So, when you are faced with a situation in which you must calculate the work done by a force, you can use equation 8.1 as long as you only use the component of force which is parallel to that motion. Well, how would you do that? You can take any force vector and use trigonometry to split it into its components. Then you can find the component that is parallel to the motion and plug it into equation 8.1. Even though such an exercise should be old hat to you, I won't require you to do it in this module. After all, in Module 7, I promised that you would see no trigonometry in this module. As a result, in all the situations of Module 8 that I present, the force will be parallel to the motion. Nevertheless, you have to remember that only the parallel component of the force counts towards the work, and I expect you to understand why. Now that I've gone through the concepts behind equation 8.1, it's time to get into the heart of the math. First, let's talk about the units involved. The SI unit of force is the Newton, for sure. Here we go, the force in newtons. And the SI unit for distance is meter. Thus, when I calculate work, I take newtons and multiply by meters. This gives me a Newton meter. And in honor of James Prescott Joule, a brilliant British physicist who did pioneering research in the study of energy, we call this unit the joule, which is abbreviated by capital J. Since the joule is a metric unit, we can also add prefixes to it. Thus, kilojoules, centijoules, and megajoules are all legitimate energy units as well. Also, you must remember that the joule is simply the SI unit for work. In order, any force unit, pound, newton, dyne, etc., multiplied by any distance unit, inches, centimeters, feet, etc., is a valid energy unit. The standard energy unit in the English measurement system, here we go, is foot-pounds. All right. Now, let's work on your own 8.1. A gardener is expanding her garden. In order to do this, she must push a heavy rock out of the way. She pushes the rock straight in the direction that it travels, moving 451 centimeters. If she does a total of 34.5 joules of work in the process, how much force did she apply? This is pretty much a straight plug and chug. So we have our delta X in 451 centimeters, red flag. We know that has to be meters. So I did the conversion here. It tells us the work was 34.5 joules. And we're trying to figure out how much force that she applied. So work is force parallel times delta X. We're solving for force, so the equation becomes work over delta X. You put your numbers in, you get a force of 7.65 newtons.